Hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session, we shall see how to analyze a portal frame with the help of Kanis method. So for that, I have considered a symmetrical frame over here. And whenever we are having a symmetrical frame, we have learned from previous class that we need not consider the lateral sway component into the consideration while analyzing the symmetrical frame. And if you observe the length of the column over here, CD is also 4 meters and AB is also given as 4 meters. And if we cut exactly at the center, we are getting an identical mirror image. So based on this one, we can call this frame as a symmetrical frame. So if you want to analyze this particular frame by Kanis method, we know from previous classes, the first step involves to calculate or to find out the fixed end moments. See here, if you observe, the span AB and CD is not carrying or not having any external loading. So, the fixed end moment from A to B and the fixed end moment from B to A, also the fixed end moment from C to D and the fixed end moment from D to C is equal to 0 since there is no external loading. So now if you want to find out the fixed end moment for span BC over here, for span BC, so the fixed end moment from B to C, since we are coming from left to right and whenever we are having a central concentrated load, we know the formula which is WL upon 8. Since we are coming from left to right, the sign convention here will be negative. So here W is given as 100 and the span over here is total 6 meters upon 8, which will be equal to minus 75 kilo Newton meters. So fixed end moment from C to B, the formula remains same, only the sign convention changes since we are coming from right to left. Now it will be plus WL upon 8, which will be equal to plus 100 into 6 upon 8, which will be equal to plus 75 kilonewton meters. So the next step will be to calculate the rotation factors. To calculate the rotation factors, which is represented by U, and the stiffness, which is represented by K. So to find out the rotation factor and the stiffness, let us consider a table over here where I will consider first the joint, and for that particular joint we shall consider the members, and for that particular member we will find out the relative stiffness, which is represented by K, and also we shall find out the total stiffness about the joint, which is represented by sigma K, and the rotation factor, which is represented by U, is equal to minus half into K upon sigma K. See here, if you observe in this frame over here, we are having two joints over here, that is B and C. So if I consider two joints, which is joint B, see if you observe here, joint B is connecting for B to A and for B to C. So here we are getting two members, that is BA as well as BC. See, whenever we want to find out the stiffness, we know that we have to consider the far end conditions. In this particular member BA, B is the near end and A is the far end, and since A, the far end is fixed here, the stiffness is equal to I upon L. So since I is already given here, which is 2I upon the total length here is 4 meters. So here it will be equal to 0.5 I. So next, for member B to C, B is the near end and C is the far end. Since C is an intermediate support here, in structural analysis, even the intermediate support also is considered as a fixed support. So for fixed support, it will be I upon L. So the moment of inertia they have given here is 3I upon the total span here is 6 meters. So which will be equal to 0.5 I. So similarly for joint C, if we consider, see here, C is connecting for a member from C to B as well as from C to D. So here we are having two members, that is C to B as well as from C to D. C is the near end here and B is the far end here. Since the far end here is an intermediate support is considered as a fixed support, so the stiffness will be equal to I upon L. So here it is 3I upon 6, which is equal to 0.5 I. So for CD, C is the near end and D is the far end. Since the far end is fixed over here, the moment of inertia, the stiffness will be equal to I upon L. So here I is given as 2I and the length is 4 meters. So we are having 0.5 I. So now if we take the summation of these two members, that is BA and BC, we are getting the total stiffness, which is equal to I. Here also for member CB and CD, it is the stiffness, the total stiffness is equal to I. So now if you want to calculate the rotation factor, which is given by U is equal to minus half into K upon sigma K. If we just put the values over here, we are getting the value of here this one. For member BA it is minus 0.25 and for member BC it is minus 0.25 and for member CB also it is minus 0.25 and for CD also it is minus 0.25. So here the next step will be to calculate the rotation contributions by the help of iteration process. So for that I have considered a table over here, which is also called as Kanis table, where I have replaced the intermediate supports with the help of boxes, which is called as Kanis boxes. So this is A and this is B. Here it is C and here it is D. So now what we have to represent in this Kanis table here is whatever we have calculated the fixed end moments in the first step, we have to represent the fixed end moments in this table. Also we have to calculate the summation of the fixed end moments whatever we are getting at this particular joint over in this box here. See here, the fixed end moment in the first step from A to B we have got is 0. And for B to A it was 0 and for B to C it is minus 75 kilonewton meter. I am writing only the values and not the units over here. So from C to B it is plus 75, C to D it is 0 and from D to C the fixed end moment is 0. See here, now if we take the summation of these two fixed end moment over here, it will be equal to minus 75 and summation if we take about plus 75 and 0, the summation here is equal to plus 75 kilonewton meters. So now if you want to calculate the rotation contributions, which is represented by small m dash, here m dash AB, here m dash BA, here it will be m dash BC, m dash CB, here it will be m dash CD, here it will be m dash DC. So since we know that the rotation contributions is calculated only for the intermediate supports and not for the end supports, the rotation contribution about the end supports will be equal to 0 over here. From the previous class we have learnt that if we need to find out the rotation contributions, which is given by the formula, U is equal to m dash is equal to U into summation of fixed end moment plus summation of far end rotation contribution. So this is the formula we have to use whenever we are calculating the rotation contributions. So if we go for the iteration process, considering the first cycle over here for m dash BA, so m dash BA over here will be equal to the formula U. See, they have given U here. So U means it is the rotation factor, whatever we have calculated in the second step. So that rotation factor we have to represent over here, which is from B to A and B to C. Here in this box we have to represent C to B, and here we have to represent the rotation factor, that is C to D. So we have got the rotation factor over here from step 2, which is minus 0.25. Here also it is minus 0.25. Here it is minus 0.25, and here also it is minus 0.25. So these are the rotation factor whatever we have calculated in the second step. So just putting the values over here, the rotation factor, which is minus 0.25 into summation of fixed end moment about this point. Here it is minus 75 plus summation of far end rotation contributions. See here, for m dash BA, for joint B, this is the far end here, that is m dash AB, and also m dash CB. This is the far end here. For C, it will be m dash BC and m dash DC are the far end here. So if we take the far end rotation contributions, here already we know the value is 0, plus the far end rotation contributions m dash CB, we don't know, we need to calculate. So for the first cycle it will be 0. So we are having a value of 18.75 kilonewton meters. So this value will put over here, which is 18.75. Now calculating the rotation contributions for m dash BC over here. See, the value remains same for the first cycle, minus 75 plus 0 plus 0, because rotation factor here also is minus 0.25. So everything remains same. The value will be equal to 18.75 kilonewton meters. So this value over here we have to write here, which is 18.75. So next, m dash CB. See here, the rotation factor here is how much? Minus 0.25. So minus 0.25 into summation of fixed end moment. Here the summation of fixed end moment we have got, which is plus 75. And here if we see the far end rotation contributions, here we have got a new iteration value, which is plus 18.75 plus 0, because the far end rotation contributions about m dash DC here is 0. So we are having a value of minus 23.44 kilonewton meters. So this value will put over here, which is minus 23.44. Again for m dash CD, the values remain same because the rotation factor here is also minus 0.25. So all the values remain unchanged over here, plus 18.75 plus 0, which will be equal to minus 23.44 kilonewton meters. So this value will put over here, which is minus 23.44. See, we have to go on continuing the iteration process until we are having the same values over here. So what we will do here is, everything remains same, only the far end rotation contributions keeps on changing. So the rest, all of the values will remain unaltered over here. See here. See, if we take m dash BA over here for this one, the rotation factor remains same. The summation of fixed end moment remains unaltered. Only the far end rotation contributions only changes. For here it is 0. and here we are having a new iteration value, so it is minus 23.44, which will be equal to, we are having a value of 24.81 kilonewton meters. So this value will put over here, which is 24.81. So similarly here minus 23.44, here also we are having 24.81 kilonewton meters. So this value will put over here, which is 24.81. And here if we take the far end rotation contributions, here is m dash dc is 0. Next we are getting a new iteration value over here for the far end rotation contribution, that is plus 24.81. So we are having a value of minus 24.90 kilonewton meters. So now this value will just write here 24.90. See here also the value remains same, which will be equal to minus 24.90 kilonewton meters. So again this value will write over here, which is minus 24.90. See now if you observe over here, the values are not similar and the values are changing. So we have to go on continuing the iteration process until we are getting the similar values. So this was second cycle. So now going for the third cycle. If you go for the third cycle, everything remains same except the far end rotation contributions. See here. So here it will be 0, and here we are having the far end rotation contribution, we are having a new value which is minus 24.90, which will be equal to 24.98 kilonewton meters. So here it is 24.98. So here also minus 24.90, which will be equal to 24.98 kilonewton meters. So this value also we will just add over here, 24.98. So if you want to find out m dash CB, the value, the rotation contribution about here is 0, it is m dash DC, plus the new iteration value which is plus 24.98 kilonewton meter, which is equal to minus 25 kilonewton meters. So this value will put over here minus 25.00. So here it is plus 0 plus 24.98, which is equal to minus 25 kilonewton meters. So here again we shall write minus 25.00 kilonewton meters. See, almost the values are similar over here. Maybe in the next cycle, that is fourth cycle, we are going to get a similar value. So going for the fourth cycle, see here, here it is 0, the far end rotation contributions, minus the new rotation contribution of the new iteration value here is minus 25, which is equal to, we are having a value of 25 kilonewton meters. So here the value will be equal to 25.00. So here also it remains same, minus 25, which is equal to plus 25 kilonewton meters. So this value will add over here 25.00. So here plus 0, this is the far end rotation contributions over here 0, and the new iteration value whatever we have got here, that is plus 25, which is equal to, we are having a value of minus 25 kilonewton meters. So this value will add over here minus 25.00. So here 0 plus 25, which will be equal to minus 25 kilonewton meter. So this value will add over here. So if we observe now in the fourth cycle, we are having a similar values. Here 25, 25, 25, 25. Here it is almost 24.98, 25, 24.98 and 25. So if we go for another cycle also, this value will be same. So let us consider this value as the final rotation contributions value, which will be helpful for the calculation of our final end moments. See here. So the last step, that is step 4. In the step 4, if you want to calculate the final end moments, this final end moments. So if you want to calculate the final end moments, we know the formula. If you calculate the final end moments from A to B, the formula will be fixed end moment from A to B plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. So the fixed end moment from A to B, here we have got a value, we know 0. About the near end rotation contributions is also 0. M dash BA, the far end rotation contributions, how much we have got here, M dash BA, which is plus 25 kilonewton meter. So moment about A to B will be equal to plus 25 kilonewton meter. This is the value. Next, if you want to calculate moment about B to A, the formula will be fixed end moment from B to A plus 2 times the rotation contribution about the near end plus 1 times the rotation contribution about the far end. So MFBA, here we have got how much? It is also 0 plus 2 times the rotation contribution, whatever we have got here about the near end, that is 25 M dash BA plus M dash AB about the far end is 0. So the final end moment from B to A will be equal to 50 kilonewton meters. Same way, if you go on calculating for fixed end moment from B to C, applying the same formulas for each span. So for member that is from B to C, we are having a value of minus 50 kilonewton meter, and moment from C to B, we are having a value of 50 kilonewton meters, and from C to D, we are having a value of again minus 50 kilonewton meter, and moment from D to C, we are having a value of minus 25 kilonewton meter. So these are the values. So based on these values, if you want to calculate, if you want to represent the shear force diagram and the bending moment diagram, we will write over here once again. See, whatever the values we have got in the final end moments, if we just represent over here, the fixed end moment from A to B we have got is in the clockwise direction, which was 25 kilonewton meters. So from B to A we have got a positive clockwise moment, which is 50 kilonewton meters, and from B to C we have got anti-clockwise, which is 50 kilonewton meters, and from C to B we have got positive 50 kilonewton meters, and from C to D it was anti-clockwise over here, which is again 50 kilonewton meters, and from D to C we have got a value in the clockwise, in the anti-clockwise direction again. Here it is anti-clockwise, it is minus 25 kilonewton meters. C to D it is anti-clockwise, sorry, here it is negative, which is minus 50 kilonewton meter. So now if you want to write the shear force diagram and the maximum bending moment, see here, for span AB and span CD we are not having any loading over here, but if we take span BC over here, for span BC, if you want to calculate the maximum bending moment, so if we take this point as E, so moment about E, since it is a central concentrated load, the formula we know, which is WL by 4. So W here is 100 upon the total length is 6, sorry, into 6 upon the total, which is 100 into 6 by 4. So here the value will be equal to plus 150 kilonewton meters. So now if you want to represent over here only, see here I will write just one more diagram over here, because we have to consider each member separately to represent the shear force diagram. Here if we take for member A to B, here it is 25, whatever we have got the value over here 25, and here it is 50. So we can write here in this way, for member A to B, this is B and this is A, and if we take the span B to C over here, we are having a 50 here and here also 50. So this is 50 and here also it is 50, and the maximum bending moment, how much we have got here, 150, since it is a at the mid support here, somewhere here I will consider. So this you can join over here like this. So this value over here, it will be how much, 150 kilonewton meters. So this is B, this is C over here. So if we take one more member over here, that is from C to D. So from C to D we know here it is, at C here it is 50, somewhere here 50, and D is here 25. So if we join over here, it will be something like this. So this is the shear force diagram and the bending moment diagram, whatever we can represent by using the values with the help of the final end moments. So similarly we shall see few more problems related to frames, how to analyze the frames with the help of Kanis method in the next coming classes. Thank you.